Shrinking and expanding gaps. Some motion-based word problems involve two travelers moving toward or away from each other. Some very basic rules make these problems much easier. So it turns out what we're going to learn in this lesson is a valuable shortcut that will help you in many motion questions. First of all, let's think of some basics here. Two travelers are moving in opposite directions. Well, if they're moving in opposite directions, we always add the speeds. The speed at which they're approaching, or the speed of the gap between them, is always the sum of their speeds. If the two travelers are approaching each other, then the sum of the speeds is the speed at which the gap is shrinking. If the two travelers are moving away from each other, the sum of the speeds is the speed at which the gap is expanding. So we'll have to think about the details of the problem to figure out whether a gap is shrinking or expanding, but as long as the direction is opposite, we add the speeds. Now, if they're moving in the same direction, we subtract the speeds, and we always do bigger minus smaller just so we get a positive number. If the faster traveler is in front, that means, of course, the faster traveler is pulling away from that slower traveler. Then the difference in speeds is the difference at which the gap is expanding. Over time, the faster car is going to get further and farther from the slower car behind it. If the slower traveler is in front, then of course the faster car is going to be gaining on it, and it's going to be catching up, and eventually it's going to pass the slower car. The difference in speeds is the speed at which the gap between them is shrinking. So again, we have to think about the details of the situation, think about shrinking and expanding, but as long as they're moving in the same direction, we subtract the speeds. Okay, here's the big idea. In a problem in which a gap is obviously shrinking or expanding, we could set up a d equals rt for each traveler, but often it saves time to set up a d equals rt for the gap itself. Often just setting up that one d equals rt for the gap itself is enough to give us enough information that we can solve the question. If we figure out the speed at which the gap is shrinking or expanding, we can relate the two individual speeds by simple addition or subtraction, as we've seen. So here's a practice problem. Pause the video and then we'll talk about this. Okay, a car and a truck are moving in the same direction on the same highway. So same direction, we subtract the speeds. The truck is moving at 50 miles an hour. We know that speed. The car is traveling at a constant speed. At 3 p.m., the car is 30 miles behind the truck, and at 4:30, the car overtakes and passes the truck. What is the speed of the car? So in that time from 3 p.m. to 4:30, which is 1.5 hours, in that time, the car closed a 30-mile-per-hour gap. So we're going to focus on the gap itself, and we can figure out the speed of the gap just by r equals d over t. Of course, the distance is 30, the time is 1.5 hours, divide those and we get 20 miles an hour. That was the speed at which the gap was shrinking, and that would be the difference between the speed of the car and the speed of the truck. Well, of course, the car is moving faster because it catches up to the truck and passes it. Since the truck is moving at 50 miles an hour, the car must be moving 20 miles per hour faster than that. So 50 plus 20, it must be moving at 70 miles an hour. And that way the difference between the car and the truck would be 20 miles an hour. So notice that by solving for the gap, we made this much simpler. This would have been a much longer problem if we set up a d equals rt for the car and separately a d equals rt for the truck. Okay. Cars X and Y are traveling from A to B on the same route at constant speeds. Car X is initially behind car Y, but car X's speed is 1.5 times car Y's speed. So that's interesting. So we can express car Y's speed in terms of car X's speed, or vice versa. Car X passes car Y at 1:30. At 3:15 p.m., car X reaches the destination B, and at that moment, car Y is still 35 miles away from B. So this is very interesting. So starting at 1:30, they were in the same place, and then by 3:15, car Y had opened up a gap of 35 miles. And in that time, from 1:30 to 3:15, so that's not exactly 2 hours, it's less than 2 hours, it's 1 hour and 45 minutes, or 1.75 hours, something along those lines. We want the speed of car X. Well, let's focus on that gap. We close a gap of 35 miles in, I'll write it as 7/4 of an hour. Okay, 1 3/4 is 7/4. And writing it this way makes it easy just to divide because I multiply by the reciprocal. And again, we get a gap speed of 20 miles per hour. So the difference between the speeds is 20 miles per hour. Now the question told us, we'll have x equal the speed of car x, y equals the speed of car y. We know that x equals 1.25y, and we know the difference between them, x minus y, is 20. We know that from the gaps. So now, all we have to do, we have a very simple 2 equations, 2 unknowns here. The left equation is already solved for x, so we'll just plug that right into the right equation. Subtract 0.25 is 1/4, so we'll multiply by 4. We get y equals 80. And then that means that x must be 100, and that is the speed of car x. Notice we made that problem much easier thinking about the gaps. Finally, focus on this problem and then we'll talk about it. Okay, cars P and Q are approaching each other on the same highway, moving in opposite directions, so we add the speeds. Car P is moving at 49 miles per hour, car Q is moving at 61 miles per hour. Very good, so we get both of the speeds. At 2 p.m., they are approaching each other and are 120 miles apart. Eventually they pass each other. At what clock time are they moving away from each other and 44 miles apart in the other direction? So this is interesting. So they're starting out approaching each other, and they're 121 miles apart. Then they meet each other, then they pass each other, and at the end, they're 44 miles apart. And so we could treat that as 2 different legs, but here's the real slick thing about this question. The gap that's shrinking will be shrinking at a speed of 49 plus 61, and then the second gap that's expanding will also be expanding at a speed of 49 plus 61, because the whole time their speeds are in opposite directions, so of course we're going to add the speeds. So we can actually just add the speeds and treat it as one big distance, 121 plus 44. The shrunken gap and the expanded gap both as one big distance because the speed is going to be the same. So we're going to add the speeds, and so the combined speed, the speed at which the gap is changing, is 110 miles per hour. We have the approaching gap, the receding gap. We're going to add these together for a total distance of 165 miles per hour. We're going to divide that distance by that speed to get the time. 165 divided by 110. This is 15 miles divided by 10 miles per hour. Simplifying, dividing by 11. And then divide this down, we get 1.5 hours. So in 1.5 hours it makes this change. 1.5 hours after 2 p.m., that would be 3:30. So when vehicles or travelers are moving in opposite directions, we add the velocities. When they're going in the same direction, we subtract. Again, we have to think about the situation and think in terms of whether it's shrinking or expanding, the nature of the gap. Thinking about the directions to determine shrinking or expanding. And then solving a d equals rt for the gap itself can enormously simplify these problems.